Okay, in an here is what it looks like at the bottom. You can see the rubber band, the motor, the brush structure, and the little rubber feet. And inside the beer can is another and brush structure at the top of the rubber band. And that's pretty much all there is to it. Now, the problem with rough shapes like this and rough and ready construction is that the high voltage can't build up because of the rough edges. It sprays off as corona because projections, sharp points, small radiuses of curvature cause the electric field to concentrate at that point, and the air breaks down, and so the voltage sprays off. So this machine, as you saw in the other video, could produce a small, say 1 millimeter spark, say about 30 kilovolts according to this sphere gap tables. So what I've done is I've made, with exactly the same guts, the same internal mechanism, I've made a high voltage qualified version, which you can see sitting there sparking happily away. You can get in there with a pointer. This is the Van de Graaff machine. It has the identical construction of the beer can version that I just showed, except that I'm using two stainless steel bowls for the top capacity, a good fiberglass tube for the pedestal, and another stainless steel bowl for the base. And inside there is the motor, there's the rubber band belt. All of the internals are just exactly the same as the beer can version. This is just a passive sphere. It's the same construction as that. There's nothing inside there. It's just elevated on a pedestal to provide a second sphere for the sparking gap. And then we're using the xenon flash tube to charge the capacitor bank, as we did with the other one in the other video. Excuse me. Now, you can see that the machine is producing a pretty good spark across there every 6 to 8 seconds. So it's 1, 2, 3, 4, 5, 6, 7, 8. So every 6 to 8 seconds you get a spark across there, and that's about 45 millimeters. And so from consulting the sphere gap tables at 45 millimeters with this size 85 millimeter spheres, we should be producing right around 115 kilovolts. That's 115,000 volts in every spark going across there, and that's every 6 to 8 seconds. And if you add up all of the parts here, including the battery, you're looking at about $12 to $13 worth of parts in this Van de Graaff machine to produce nearly 120 kilovolts. You can't beat that with a stick. Now, here I have a little neon bulb. It's an NE2, and I'm holding it by one leg. And what I'm going to do is approach the Van de Graaff machine with the neon bulb, and you'll be able to see there that, well, let me turn the light out. Okay. You'll be able to see that one of the terminals of the neon is glowing from the juice produced, and only the negative terminal of a neon bulb actually glows. So since the terminal that's glowing is the one that's closest to the sphere, not the one I'm holding, that tells me that my machine is polarized so that the sphere is negative and the base is positive. The other one, the beer can version, is just the opposite. The top is positive and the base is negative. And the way that you do that with a Van de Graaff machine is you vary the material of the rollers. The top material, the top and bottom rollers that the rubber band is on should be of differing materials on the triboelectric scale. And on this one, there's a Teflon roller on the top and a roller of a different plastic, the packing tape, on the bottom. And on the beer can version, there's a metal, a metal roller on the top and a plastic roller on the bottom, so it gives an opposite polarity. Okay, so now what I'm going to do is take the second lead from the ground off here, and this is going to short the capacitor bank. Whoa, yeah, baby. Okay. That's it. Thanks for watching.